Okay, so thank you for inviting us. I'm Daniele. I'm actually a physicist. I just introduced myself a bit. I did my PhD in nuclear physics. Then a couple of years ago, I joined Luca at Orobix, and I started to play with deep learning. And in the last year, I've been lucky. I had the opportunity to play with reinforcement learning with video games. So I will show you now what is it.
Play for work, not just play. Okay.
Exactly. Of course. So let's have fun. I don't know. You can just follow me. I will just show you some code. It's quite simple, and I will explain step by step, more or less. And just to show you what it's doing, basically. It's not, this algorithm is not working by magic, as Luca explained you. But there are some rules, a lot of mathematics, basically. Not complicated, but a lot of calculation. So if you want to try, I don't know, of course, then it depends on the operating system you have. You know, there is always a bit of a mess of installing libraries and so on. Somebody wants to try himself, herself, on your laptop. I can show you how to install some libraries, and you can try to teach the cart how to sustain a pole. It takes really, should be quite fast. So if you want.
What software are you using?
So I'm using, okay, as you see, it's Ubuntu, so it's Linux. I'm using Python for developing the algorithms and the models with PyTorch libraries. So I don't know if you heard about. No. Okay. So let's try from there. It was just sleeping, maybe, or. Okay, so let's start from scratch. It's quite fast if you have. Do you have Windows or?
Yes.
Okay, but it's not going to be fast actually. Probably I can tell you later how to do it. PyTorch. You can just Google it. I'm really doing the same. So the point is that PyTorch doesn't support Windows, of course. So there is a compiled package, of course, but it's not straightforward. Probably I can just show you the code, and then later on I can set you. Well, if you have a Linux or Mac, then it's a bit quicker. I don't know if you know the Anaconda distribution of Python. Then there is already a package ready with PyTorch, and it's very straightforward to install it. Then we need another package, which is Gym. Who, somebody is doing this, or? Okay, maybe we can do it later. Or I just show you how to do it yourself. It's quite fast now, just for everybody. For the sake of time, I will just go ahead. So I want to introduce you Gym, OpenAI, first of all. Probably you heard about OpenAI organization. It's a no-profit organization, was founded by Elon Musk a few years ago in 2015, with the aim of basically make artificial intelligence public to everybody. He was afraid of the risk of artificial intelligence for humanity, so he decided to found this no-profit organization just to make it as open source as possible with models, algorithms that universities and also companies, as you know, Google, Facebook, the big companies are developing quite fast. So why it's useful for me as well, because we have this package which is called OpenAI Gym. As you can read, it's basically a collection of environments. As you saw before, reinforcement learning, you need, of course, to develop a model, an agent which is able to learn, but of course you need an environment. And it's not easy to have an environment you can interact with, because you need, of course, to receive the observation, and of course a reward, meaningful. And you need to play with it. You need to tune it in order to test your agent. So we have a nice collection of quite simple, well, let's go to environments. That's not so fast. Okay, you have a collection of course, the Atari games with a wrapper, which allows you to, okay, these are the classic control, the very easy one. So usually this is the hello world of reinforcement learning. Everybody is training with, this is the first time you approach the field, usually you try with this one. And I will show you as well. Then of course also our similar classic control little games, and usually are the easiest to train it and to understand a bit the model, your model, if it's doing well or not, and so on. Then, of course, you have the Atari games with the wrappers. So you don't care too much about the environment. You just, because they provide you the observation, and it can be high level. In this case, you just get the picture, just the pixels. Or in the case of a classic control, you just get low level information. For example, the angular speed, the position of the pole, and so on. And it depends on what you want to do, basically. And they give you the reward as well, in a simple way. So there is, of course, a tutorial. So if you want to install it, then you will need just to follow this simple tutorial. Should work fine on Windows as well. Then you will have probably some problems with rendering of the environment, which is the nicest part, anyhow. So just to start, you will need the gym, this code, and then PyTorch. It's more or less everything you need just to get started, basically. So I can show a little bit how it works, just from scratch. So you just basically define the environment. You just write the name you want. You make it, and just render it. This is just a card doing something random with no reinforcement learning, of course, nothing interesting. And then what's important for you is what you get from the environment, and you provide to him, of course, the action. So you have 4 essential information, actually 3. So the observation, which can be the image or just physical information. It's just up to you. And then, of course, the reward, just to tell the agent if he's doing good or if he's doing bad. And done provides you the information to restart an episode. For example, the pole has fallen. You need to restart again. Or probably you reached the maximum number of steps, because you can keep the pole up straight forever, but the agent will not learn that much. You need to restart in another random position, so the agent can generalize the behavior in whatever position then you will start. And then additional information, which can be whatever you want. In this case, it's quite easy. Probably don't need that much, but in other environments, it's important as well. Again, this is how it works, as Luca explained. You have an agent. It gives an action to the environment to an agent who is playing in the environment. You just control it. You just provide what he has to do. And it can be discrete, can be continuous. And then the environment will provide you the observation, the new state, basically, as a consequence of your action you decide to do, and the reward, because you need to know if you're doing well or not. So I will just show you now. And then there are some more information, of course, about the action space or the observation space. Indeed, it can be continuous, discrete. You need to put some limits and so on. This is a bit more technical, and then all the other environments available. So it's very nice. And right now, it's not really well maintained, because up to some time ago, there was also a leaderboard, basically. So for every environment, there was basically a leaderboard with any algorithm you could submit, you can try. So it was kind of a competition, let's say. Yeah, down here there was a list of algorithms, because you have an environment, but you need to plug your model, your algorithm. And of course, there were some rules when the environment was considered solved or not. And it was a competition about who could solve the environment first in less episodes, let's say. Now it has been removed, and also the Atari games have some problems because the wrapper have changed, and it's a bit, this field is moving quite fast, and if you wait a few months, then it's already obsolete with your code library and so on. So I will show you a model. It's called Actor Critic. I will tell you why, which learns how to sustain the pole, basically, just moving a card. Very simple problem. Then I will move to the Atari games, which are a bit more interesting, but maybe you need a bit more complicated, let's say, model with environment and so on. So I will go. So I will go through the code. I don't know how much you could see. Try to explain, part by part, what it's doing basically. So I don't know how much you're familiar with Python. Yes, no. Yeah, it's quite simple programming language actually, it's scripting. And then I'm using, as I told you, the PyTorch torch libraries, which are basically a collection of libraries for deep learning. So all the low-level calculation, matrix, multiplication, whatever is already included in this library. And it's quite easy to develop your model exploiting this library. You just care about how to structure your model and then how to provide observation and so on. And as you can see, then the code is not that long. So let's start. Okay, you import your libraries. You very easily define your. Do you see you in the back? Okay. So you just define your environment. This is the carport. Okay, version 1 needs 500 steps to be successful. Let's start from the 0, which needs just 200 steps. 200 steps. The car can sustain the pole without let it fall down. And this is considered a success. The environment solved. When you provide a seed, a random seed, because the card can start at whatever position, and what you will see later in the Atari as well. What the agent learns depends also as he starts usually, and it's like sometimes it overfits the situation. So it can not always generalize to every possible situation. So it can learn well in some points, but not in others. So sometimes the outcome of your experiment or the behavior of your agent depends how you seeded how you started, how the environment was behaving basically as well. So, let's start from here. Okay. So here you define your model. I don't know how much you're familiar with deep learning. I will try to explain a bit more here with some illustration as well. Okay, yeah, you could not see a lot, I guess. Do you see something? Okay, it's not very important. It's carport environment is quite easy. So basically, this is the class describing it. The physical quantity, which is just defining the gravity, the mass of the cart, the mass of the pole, and so on. Then you need to specify the condition when you want to terminate the episode, and usually when the pole has fallen to a given degree. This is some more technical things. And then you need to provide, of course, the action. In this case, we have two possible discrete actions, just move right or move left. And then the observation space, which is just, which has 4 values, as Luca showed you before. And you just need to define just basically a limit high, minus I high. And then you just, okay. And that's it. Then there are some more technical things like that. Okay, you need to seed it, and then the viewer to see it, and initialize the state, and so on. So this is the environment. Now you need to define your model. This is the agent, the brain, basically. But we decide what to do. Move left, move right. What shall I do, basically? So this is a neural network. So this is basically is done exploiting the torch libraries. So you just, neural network is made of many parameters, it's called also neurons, connected each other with activation function, which can be linear and not linear as well. So what's happening basically? You get an observation from the environment, which can be 4 values basically, 4 continuous values in the range you defined. Given these values, this value will go in these parameters. In this case, 128. After this parameter, you will have an activation function. So you have a multiplication for a parameter plus a bias, let's say. And then there will be an activation function will pass the value to the next parameters, which are basically what is called the action head and the value head. So if you're used to deep learning, this is very small and very, very small and easy neural networks. And just one not even one hidden layer because it's just the input layer more or less. So you just provide basically the observation. It will go through all these with trainable parameters, and then we will output these values. After the layer of 128 parameters, we have basically two branches. The action head is responsible, is what is called the actor, because he has to decide what to do. So here you can take two actions basically, right or left. So the neural network will give me two probabilities of going on one side or the other side. The two probabilities for the two possible actions, which are normalized, so the sum is just 1. Then on the other side, that is the critic, because it criticizes the action taken, let's say, because it needs to estimate the value of the state. Basically, given the state, the observation, okay, I call it observation. It's not the state, because the state means all the environment. Sometimes I don't need all the environment. For example, if my input is an image, I don't need every single pixel of the image. Of course, some parts are way more interesting, but the black corner on the top, I don't need it. So observation is usually what the agent observes. In this case, the agent doesn't see the picture, and he sees only these 4 physical quantities, which can be enough anyhow. The environment can be fully observed even if you provide a few numbers. It can be enough to understand the dynamics, the physics, and then decide what to do. So this is just the model. So he has to basically, given the observation of the environment, decide what to do with a given probability and give an estimate of the value. So the function you see here is exactly what it does. I get x, which is the observation. It goes through this layer, 100, this 4. It goes through 128 parameters with the real rectified linear unit, which is the activation function. So it's basically, if it's more than 0, it just take the value you got from the parameters. If it's below 0, it's just 0. And then after this, it just goes to the action head and to the state value, and the other one. And of course, this softmax is just a normalization basically of the two probabilities. So this is basically our model, our agent, which has to learn what to do. And now let's see what it should do. So you define the model and just call this class. And you define the optimizer. I will show it later a bit. And these are our function. I will show it in a while. So at this point, you start to explore, to train, to explore your environment and to learn. So what does it do? Basically, as Luca told you, you have your policy. So basically, you start your training. So for a given number of steps, it can be infinite if you want. You can go as long as you want with the episodes, sorry. You reset the state, so you place the card with a pole in a random state. Of course, a feasible one if it's already fallen and there's nothing to learn. And then you start an episode, basically. So the agent he receives already the first observation, the first one. He has to select what to do. So it will select an action and also give a value to this state, which will be recorded in memory. Because, sorry, I didn't tell you, but here there is a memory buffer, basically in this class, which will record the action taken and the reward he got for every step. So for every episode during his exploration, it will record. Yeah, sorry.
I have one question. I saw that in your solution, the network is outputting the action, but also the next state, right?
Not the next state, but the value of the state. The network has a given estimation how much this state worth. For example, if a pole is almost fallen down, the model should tell me that this state is really poor. It should give a low number, basically. If a pole is straight, if the observation is, if a pole is straight up, then it should tell me that this state is it's good. I mean, it should give me high value. Exactly, it should tell me this state is good or bad, basically. I'm in a good state because the pole is straight up, okay, great, I'm doing well. Or the pole is falling down, bad.
So are you learning the policy and the value fraction?
Exactly,
at once?
exactly.
Okay.
That's why actor critic. So the actor has to choose what to do. And maybe it's a critic, but it's the same model, basically. Sometimes it's also split. But at the end, I mean, you are training to do the same thing. So usually you have an even better performance in this way. And it's a very simple model, actually. I mean, in deep learning, our deep learning models for examining images, whatever, you have many layers, way more parameters and so on. Here it's very easy. So this is the task of a model. Tell me what to do, and give me an estimation of how much is worth this state, basically. And you will see now how model can understand how to improve it, basically, in both the estimation and in the decision of the action to take. So this is this is just the coding of this scheme. So basically, he has to select the action, and in the meanwhile, record it as well. Then I will pass the action to the environment. It's just a step, so I don't care about it. This is done by the gym libraries. So this is very comfortable. I don't have to care about what's happening over there, programming that, and calculate the reward and so on. It's already provided. And it gives me the new state, the reward, and if it's the pole has fallen down or I may reach the limit in the number of steps and so on. Then of course this I added myself just to calculate the return of the episode. This is just the rendering, you will see later. And then I need to, of course, to memorize the reward. So let's dig a bit in this function. Okay, let's look at it because it's very. You see it here. Sorry, this is a very small function to select the action. Basically, it's here. You give the state to the model, and you get the probabilities, the two probabilities of the two actions, and the estimate of the value of that state. Then, here is important. You don't choose the action with the highest probability. Why? Because if you always choose the action with the highest probability, you really end up in a very, you cannot explore more. You convert to maybe a nice policy, a nice behavior, but you don't see you are missing something more. I mean, you can have a better policy. You convert to a nice one, a good one, but you will not reach the best. Imagine you are trying to reach a candy and you have some obstacle in between, which give you a negative reward. If you go to the obstacle, you get a negative reward. Then you go there and you come back because it's not good for you. And you will never reach a candy which are over the obstacles. Sometimes maybe you reach the obstacles. Then your decision it will be maybe 60% better to come back because I'm receiving a bad reward there. But the action is chosen by following the distribution of the probabilities. So for 60% of the times I will come back, but the other 40% I will go over the obstacles just randomly. And then by this random choice, I will eventually discover the candy. Then I will realize that over there is a candy, I have a huge reward, so I don't care about the obstacles next time. Even if there is a bad reward in between, I don't care because I know that later on there is a better reward. And this is very important to maintain the exploration, because in these algorithms it's always a problem, the balance between exploration and exploitation. That means exploitation following the best policy I learned so far, but also keeping exploring, because if I follow only the best policy, I do the same things every time. And this, as I told you, prevents me to explore the environment and maybe found something better. So every time the action is chosen between following this probability distribution. So, and this helps the exploration. In many algorithms, it's also, this is not enough. It's also added another parameter, which is called epsilon greedy. And then you choose a totally random, with a given probability, you choose a random action, not following the distribution given by the model, and do something completely random. It helps the exploration. It's very useful in the beginning of the training because the agent has to learn, has to explore, first of all. So it's very useful. But then it can be problematic in the end, so usually it's decreased. Sometimes it's helpful, sometimes not. In this case, it's not really. I mean, the environment is simple and it's not really essential. And then you record, of course, the action you take in the model for this episode. So let's go on. So at a given point, either I reached the maximum number of steps or the pole has fallen down. And in this case, I quit the loop. And I need, in this case, I collected the experience, so I will train my model. So let's see how to do it. Okay, this is the action in the environment. It's just the calculation of the new states given the physics, providing the reward, and then returning the new state and reward. It's just how it is made in the GIRM library, basically. It's not that complicated. I mean, it's a simple environment. So it's now time to train the model. I collected experience following the best policy I reached so far, and the first time is basically totally random because the agent doesn't know anything about the model. This is model free. It doesn't know anything at all. Not about the physics, not about he has a pole, he has to keep it straight, anything. So, first of all, let's get all the couple of action and reward he got during the episode. So here we'll have a list of couples given at every action, at every step, the action I took, and the reward I got, basically. Now I calculate the discounted rewards, the return in this case. So basically, for every step, I sum up all the rewards I got later on with a discount factor. This args gamma usually is the discount factor. And usually it's close to 1. Of course, if you decrease it, then you don't care about later rewards. You focus more on the immediate reward you can get. If you set it 1, then you care on the reward of the next state as much as the reward of the last state. But usually what happens in the last state is dependent to the given point to what I'm doing now. So usually it's a bit discounted what is happening at later point. So basically I'm preparing these returns with a discount factor. And then this is just a normalization, just to keep it stable for training. And at this point, so this is why it's called actually not only actor critic, but advantage actor critic. I calculate for every step, it's here. Okay, for every step, I calculate the difference between the return I got actually from the environment and the estimate of the state that I made. So the network, the model is comparing what he estimated that state was worth it and what he really got. Of course, the best will be advantage of 0. So the model is able to correctly estimate the value of each state. So it calculates for this advantage for each step. And then it will basically collect these advantages to then update the model, the parameters. So the model needs to improve the policy. So it needs to improve the capability to choose the best action, which will bring to the best state, and finally the best performance, and both the value. It must be able to correctly estimate the value of each state, because if it's able to do that, it's also able to do the right action. And if it is able to do the right action, then it will be able to reach the best performance. So I'm basically collecting all the policy losses, which is given by the logarithmic probability times the advantage. So more or less means that if I have a big advantage, so that means that I had a big positive advantage. That means I had a poor estimate of a state which had a high return, and I had also a small probability to do that action which brought to that state. Then I have this loss quite huge, basically, right? and we will be when we select a big loss, we'll then bring it to a big gradient, and will do a big correction to my models, to a value of my parameters. And then again, I need to basically decrease the difference. Smooth L1 loss is a slight variation of the mean square error, more or less. It's a bit more stable with just some adjustments. Basically, I need to decrease the difference between the value estimated and the return I got. So I need to minimize these functions. So at this point, exploiting the libraries from PyTorch, I can just do the training in a few lines. So the optimizer is basically, as it was shown before, it's Adam. It's called Adam, but it's basically a variation, an optimization of a stochastic gradient descent. So basically, you follow the gradient of the function, of the loss function, more or less. And you make, at every step, a small update of your parameters, follow the gradient, to minimize this function. With a rate you choose. The learning rate is essential, usually in these models. So you zero the gradients, then you calculate then given the loss, which is the sum of the policy, of both the policy and the value. And then you go backward, you exploit the back propagation, you update basically all the parameters going back from the last layer to the first. By here, it's basically 3 layers with an optimizer step. You just make a little step and update the parameters. So at the end, the parameter should be improved in order to choose every time the best action, and which brings me to the highest return, and of course improve the estimation of the value of each state. And then at the end of the training, I just reset the memory buffer for the rewards and for the actions. So at the next episode, I will collect everything again. At the end of the episode, I will do the same thing, update again all the parameters, and step by step, the model should improve, basically. That's it. So let's try to run it, basically. Is everything clear or questions? Okay. So, okay, what your cannot really. Okay, I cannot zoom. I don't remember the shortcut. View. Okay. So what you're seeing? Okay, the model is training. So at episode by episode, here it's log every 10 episodes. You see, okay, the last length of the last episode of the 10 episodes, and you see how long this episode lasted. So here the reward is very simple. It's just +1. Every step the agent can survive. So if it can just stay in the environment, that means the pole hasn't fallen yet. So basically, if the agent is learning something, I should see an increase of the length of the episode, basically. And this is basically the running average. I'm just summing up and averaging every time. So basically, after not so many episodes, a few hundreds, okay, this is the version 1. So the limit I set is 500 steps. So if the agent can reach 500 steps, can survive 500 steps in the environment, the experiment is considered solved, basically. Of course, sometimes it can reach it, sometimes not. It depends how it starts. It depends on the action it takes, because there is also the probability of the action is taken or not, and so on. But after a while, if the model can converge to the optimal policy, the probability of taking the right choices should be 90%, 99%. It depends on the environment, of course. So, okay, now it's done. This is not so exciting, actually. You could see it's learning while it's basically graphically, although it's a bit slow, so let's do it every 100 steps somehow. but okay, well, it should be fast enough actually. So in the beginning, he's struggling to keep it right. He's doing almost randomly. It will take a while now because it's much slower. So it takes about, I don't know if, okay, at 200 episodes, it starts to do something. Okay, do you have any questions meanwhile? So this is really the basic. I mean, it's a simple environment. It's a very simple model actually. I mean, the idea behind is very powerful. It's because it can do it. It can solve really complicated environments. This is very easy, but the same model with maybe one more layer, some a bit more complicated. You can add also some other recurrent network and so on. But this model can solve rather complex environment, both from raw pixel of low-level data, but with sometimes not 100 episodes, but dozens of thousands, it can reach a decent policy. So this was basically the, okay, now it's doing a bit better. Okay, so this is the advantage actor critic, and this is, I think, as far as I know, still one of the best model used for for reinforcement learning and for deep reinforcement learning, because it's, again, deep learning, which is basically the small model I show you, the neural network with the strategy of reinforcement learning. And it's still one of the best algorithms. The asynchronous version was published a couple of years ago still from DeepMind. It could beat the performance of a DQN model on the Atari games. And it's still, as far as I know, one of the best in solving not only the Atari but other problems. It's the model that can generalize most. There are other models better in special game, special situation, but this is still one I can generalize best. Okay, now more or less can keep it straight. And it just learned from scratch. I mean, it didn't know anything about the environment, nothing. Totally model-free, basically. So let's see now something more exciting with the Atari. So the model is still the same. It's actually called A2C. So it's advantage actor critic, but it's a synchronous version. So there are many, basically. Here there was just one agent exploring the environment. Once the exploration is finished, the episode is terminating, doing the train, and then one after the other. If you want to speed up the training, it's better to have many agents exploring the environment independently, so you can explore the most as possible, and then at the end just train a single model, a single brain basically. So just many agents exploring, doing whatever, and then training a single model. So with an average of what they collected, and then with a new policy of this model, just again explore and so on. And you can train especially complicated environment much faster. So I can show you. Okay, since the OpenAI baselines are a bit broken now, there is no more trained. There are no more trained models with Atari, and it's not even straightforward to download everything and make it work. I mean, these models are very sensitive to hyperparameters, the observation, the reward, and so on. It's very critical. I mean, in my little experience, it's, I mean, just a slight variation of each of the reward, of the observation, of the hyperparameters, the learning rate, the number of parameters, whatever you want, can really choose between a very nice performance and almost nothing at all. So this is a repository you can find online. I will show you. It's basically the same as before, but it's a bit more technical because now we'll have more agents exploring the world. And so many models working in parallel and then updating the same unique model. But okay, I will not go in the details. So I can just show a bit how the results, and then let's try to train one. It shouldn't take too long. And you will see how to monitor basically the progress. So let's just see the breakout, an agent, an actor critic, the same model you saw before. I trained this afternoon for, I don't know, 1 hour or so. And this is what it learned. It's still not the best policy, as Luca told you before. It was really impressive because the guy learned to basically dig a bit just in the corner, basically on the side, to send the little ball just on the top there and let it basically bounce everywhere and clear the game, basically. So it was basically, of course, the best policy. It's the best you can do. At this point, he didn't learn it. He just learned how to play, and it's still impressive. Just from this, in this case, just from the image, from the raw pixels. Yeah, now he managed. He's trying, he's learning now how to do it. As you can see, he tried all the time to send it over there. So it's the best move you can do. I mean, you get a lot of reward. And that's it. I did breakout and Pong as well. Should have it somewhere. I think. Okay, and this is, okay, the green one is the agent. And you learn how to play Pong, more or less. Sometimes, but it's nice that you learned some moves, not so many, and you always win with some moves. For example, this one. He knows that he cannot reach it, so he just stays in the bottom. And after a while, it's always the same. It's a bit boring because he knows what to do. It's very robotic, let's say. But if you provide, if you describe the problem as it is, and you provide the right reward, then sometimes you find that the agent is not stupid at all, and he learns some policy that you didn't even imagine. And this is very efficient. Okay, then of course the initialization of the environment is always the same. That's why I changed the seed and just a bit more variety. But after a while, it's not human-like because it keeps moving and bouncing, but again, he knows what to do. Okay, also in this case, you provide, as observation, you provide 4 frames of the environment. So you stack together 4 images, basically. In this way, you can infer the speed, the direction of the board, basically. Otherwise, it's impossible. It will never understand how to do it, basically, because it doesn't have any access to the physics. It's model-free again. It doesn't know what to do. There is no extraction at all. So it needs all the necessary observation to understand what to do. Otherwise, it's impossible. And it's not easy sometimes, especially if you go with low-level observation with just some physical parameters. Then you must be sure that you're providing everything. In this case, you provide 4 frames every time. And then again, it's the actor critic, as I described you before. It decides what to do, move up or down in this case. Nothing more, it's quite simple. And then give an estimate of a state. And again, and then training episode over episode. And now we can just start the training if you want. There's nothing really exciting, but let's do it. The nice thing that you can I don't remember now. I need to check the instruction as well. And I want to show you as well what we are doing in Orobix with this reinforcement learning. I should have it somewhere. We are now working on including the reinforcement learning in a video game, basically, in a racing video game. So we developed, based on the gym environment, we've developed an environment for ourselves with all the observation and reward we need, just to train a car basically to race, to go as fast as possible, and also deal with opponents. So that's better to see it. So the agent is the red thing here, and this is an opponent basically, which is still okay. Every time he's passed, he's placed in front again and again, just to favor the training. Otherwise, he has to complete the turn and again found him and understand what to do. So the agent learned from scratch again with the actor critic model, the model I showed you before. It doesn't know anything about driving. He has to decide at every step if turning right or left, and with a given amount, and accelerate or brake. He doesn't see an image. He just sees some information relative to the circuit, basically. So its speed. The red line is basically where he will go if he follows this direction. So with a few physical information, he's able to learn how to drive and also to deal with opponents, basically. This is another secret. This is a bit more traffic. So he has to understand when to wait, when to accelerate, and he has to go as fast as possible. It's not enough just to travel quietly, but he needs to win the game. I mean. So that's it. And with some, it's a bit more complicated in the card poll, and especially the video game is way more complicated as well, because the physics here is an approximation, but the video game, of course, the approximation is much more accurate. So, but it successfully learned actually how to drive, at least in the simplified environment, and to drift as well. What you see here, the blue line is basically the velocity, the physical velocity. So where he's going. So sometimes when he goes fast, he's drifting. And that's it. So, okay. Let's try to, maybe we can have a break and eat something while the agent maybe is training. So, okay, this is a nice repository, not done by me, by this nice guy with a difficult name. And okay, it's not straightforward because installing OpenAI baselines and whatever, it takes a bit of time. But he implemented some common algorithms. The A2C, the advantage actor critic, I don't remember this is the actor, which is again actor critic with a chronic thrust region and so on. So, okay, this is just to see, I had to have a monitor basically of the training, because what can I look? How can I check if the agent is learning something or not? I cannot wait many days sometimes, even a week, and then at the end find if it's learning something or not. So I can simply check at every step, basically, not every step, every episode, how much return he got, because this he has to improve. He has to collect as much as possible. So let's start this. Okay, maybe do it here. And now let's do the Pong, or I don't know, the one you prefer. Let's do the classic one, because it doesn't take too long at least. Okay, I don't have a list, the last version of a gym, but whatever. Okay, of course I have a monitoring on the screen. Basically, after, I don't know, every 10 episodes as well, I see what is going on. The number of time steps is managing to survive, more or less. Then the reward is getting, again, maximum, minimum, whatever. The entropy is, okay, something less. The loss function on both on the value and the policy. And it's a bit more nice. Why didn't I start? Yeah, probably should restart it, but forgot. Well, you will just see a plot with a return increasing. That's it. There's nothing. Yeah. Any question? Any something not clear at all? For sure. Yeah.
Usually when you have, let's say, convolutional neural network, it's pretty clear if you are overfitting or underfitting your stuff because you have a number of parameters, a number of images, and so you know if your network is too big. Here, how do you have this kind of problems, or how do you do this kind of problems? Because as I understand it, you update your loss each episode, right?
Yes.
But you have fixed parameters for your network, so
We are not.
many episodes you are fitting on it's like fitting on many images for convolutional neural network.
Yes.
So there's no danger of overfitting or underfitting.
The risk is to overfit the episode. The environment. Because if the environment is not various enough, I mean, it's always the same thing. When the agent, the neural network, learns how to deal with that situation, once there is another situation slightly different, but he never met, then the risk that he doesn't know what to do. When he really, it's a disaster, basically. So the risk here is to overfit the environment, basically. It should be as various as possible, let's say. That was your question, I mean. Yeah, even also because the model is quite simple. As you see, it's just one layer. So the risk is quite high as well. But deeper models don't perform well. I mean, you can add 2-3 layers, but it doesn't learn anything. At least when I try, but I saw in the literature, usually it's 1-2 layers, 400 parameters, maybe some LSTM cells on top, some variation, but usually no dropout unless you have some imitation learning, so you have supervised learning combined. But if it's just this model, it's just a few layers. With, of course, convolution here, I didn't show you the convolution layers because I was just taking some numbers, basically, from the cardboard. But otherwise, there are just a few layers of convolution, and then fully connected, and that's it. But still very, very simple. Okay. It's still in the beginning, so the rewards is quite bad. It's negative still. It's losing all the... And we can actually have a look what is performing right now. Just if it doesn't crash. At this stage, I can just take it was the Pong. Okay, I should have been overwritten, so I think this is a bad one. Yeah, let's see. Yeah, it's not doing anything. So now it didn't learn anything so far. And yeah, you can see it here. I mean, it's not improving because it's still very well, it's even getting worse. You should be patient, basically. It takes a while. In this case, we need to wait half an hour, let's say. But at this stage, as you see, it doesn't do anything. It just stays there. And there are many agents exploring the environment. You see it here. So it's even computing intensive. Well, not so much, it's not a big deal in this case, but this speed up a lot the training. The asynchronous way, I mean, was tried by OpenAI as well, but we didn't get a lot of that advantage that was claimed in the paper as well. But anyhow, having many agents can improve, at least can speed up. The performance at the end maybe is the same you can reach with a single one, but let it train.
Pizza is here.
Yeah. Thanks a lot if you don't know it.
So you said the models are usually simple. So my question is, where are the critical points when you're using reinforcement learning to solve a problem?
Okay, well,
Do you have time?
Yeah, I do.
at least the problem I met myself. I mean, it's the right observation. Sometimes you just, if you don't provide the full image, which sometimes it's too much, it's the easiest way because just throw the image and then the agent will learn what to do. You don't care. I mean, just provide everything in that case. Sometimes it's a bit too much. I mean, because on that image, it just needs a little part. In the Atari, maybe not, it needs the full picture. But in my case of a circuit, maybe it's easy if it is seen from the top or just in front. I mean, sometimes it doesn't care, especially in a video game, which is the reach of other features like the public and so on. It's even disturbing for the agent. So the right observation. If you don't go by images and there is everything maybe too much, then if you go with numbers, with physical quantities, then you're not providing enough, basically. In my case, the car was not learning anything because basically didn't know how to plan a turnaround, basically. Because the reward, in that case, the reward is how much road you travel and in the last time. So every step you get a negative reward, and at a given, you divide the circuit in many parts, and as soon as it reaches a part, it gets a reward much higher than all the negative reward he collected at that point. So he has to go. He has to stay in the environment as less as possible because every step is minus something, and he needs to reach this pieces of circuits basically to get something. So at the end, what happens is just it goes as fast as possible. So the reward, because if you just say do as much road as possible, it just goes slowly. There's nothing that pushes him to go fast. It's even dangerous because it goes out of the circuit. So observation, and then the red line you saw in the environment is just the future position the car will be if it keeps that direction. So he knows even before the turnaround that if it goes straight in direction, if it is now, it will go out. So he can plan a little bit. So, but it's critical, I mean. And it's just 30, 40 numbers, and he can drive. In this case, he has to take two actions as well. Steering and accelerating and braking. And in the beginning, it doesn't know anything, so it just do randomly, and it takes a while also to learn. But that's this critical observation, the reward, and the hyperparameters, the learning rate, for example. You just change, really, 10%, it doesn't learn anything. You change it, and then it goes and learns. And it's very unstable. I mean, even the serious people trying to do important stuff, they're usually trying to replicate the results they showed in the paper and so on. It takes really a while. Even OpenAI struggled a little bit to replicate all the results DeepMind showed, and they found also differences. And then you must be sure that your environment hasn't any bug, and that's it. There is also in OpenAI. Now it learned something. Now it understood what to do. So the rewards, basically, it's skyrocketing. If there is a little bug somewhere, it's really hard also to debug because you have no idea if it's your hyperparameter that is because it's not learning or something else. But in my opinion, the model is very powerful, although quite simple. The idea behind is very powerful. And providing the right data, it does something really interesting. I don't know if it's...
Yes.
Okay.
Okay, we can start. And maybe you can
It's
come
still,
up for other
it's still moving at
questions.
least now, but
Yeah.
it's still missing the